Welcome to everybody. This is a new session of the webinar by the Reservoir and the Labs concept. We have Mr. Derrick Green, the subject of this seminar is basics of NMR and use of laboratory NMR to help interpreting NMR logging data. I think we can leave all the space to this seminar to Derrick Green. As usual, this presentation will start there. It will start now, and more or less the duration of this presentation more or less in 1 hour. After that, we're going to have a question and answer session. As usual, prepare to jot down your question via remote chat. I will read the question and then we provide a reply. So we're going to have a discussion over here in the mosaic room. Of course, all the attendees here will follow the question and speakers will provide a reply. I think we can start. Mr. Derrick, please.
Okay. Thank you very much. Just a brief background on myself. I'll introduce myself. I'm the Chief Technical Officer at Green Imaging Technologies, and our company software in the form, we write applications in the form of software for NMR laboratory equipment. NMR laboratory equipment is designed to help understand the reservoir fields and the logs and sorts of things. So my experience is in that area. I have degrees in electrical engineering and magnetic resonance imaging, and I've been the Chief Technical Officer for the last 6 years at Green Imaging. So we'll just get going. Our presentation will give an overview of core analysis techniques. I'll try to focus on how those core analysis techniques can be used to help understand the reservoir and understand NMR logs as well. So what we're trying to do is just understand the complete picture of the reservoir and how NMR fits into that picture. So this is a very simplistic diagram of where core analysis fits in the whole routine. The whole goal, of course, is to find oil and gas, but then, of course, to characterize the reservoir so we can predict production and know the reservoir size. And I see this as a cyclical program during the life of a reservoir. So a lot of you will be familiar with this, but core analysis fits here, defining the reservoir simulators or reservoir models. So NMR would fit in this portion of the cycle. So I have a lot of time describing NMR, even though the talk says the basics of NMR. By basics, I'm just going to do just a few things that you need to understand in order to help understand how NMR can apply to NMR logs and NMR core analysis. So in components, first thing I'd like to say is MRI, which is magnetic resonance imaging, and NMR, which is nuclear magnetic resonance. They're the same thing. The medical field doesn't like the word nuclear, so it just rid of it. So it's magnetic resonance. So magnetic resonance imaging is typically used in medical fields. This is a metal scanner. Components are a magnetic field gradients. In other words, we alter the magnetic field linearly in the sample, and radio frequency coils to place energy in and out of the system to detect the signals. And there's a lot of other components I won't really get into, but this is the basics of a machine. For analysis, the equipment is quite different. So the diagram is a logging tool. It's probably quite an old logging tool at this point. This is an NMR logging tool in which you drop it down the hole and do a wireline log. Do some of these NMR measurements that I'll describe in a few minutes. The laboratory equipment is quite different. It's desktop based. You can see, so these are some of the older models, but it's smaller equipment to measure sort of 1.5-inch core plugs. You can have larger equipment to do whole core as well. So people care about NMR and core analysis, well, in medical for that matter. NMR is unique in that the signal we can get from NMR comes from hydrogen. So in the simplest sense, anything with hydrogen, when we place it in a magnetic field, it will exhibit a property that allows us to detect how much hydrogen's in that sample that's in the magnetic field. So in human beings, that's quite important because human beings are mostly water, so we can measure the water, the fat, all kinds of things. In oil and gas, of course, also quite important because we're interested in water and hydrocarbons, right? So gas and oil, so we can see those signals. So in addition to seeing how much hydrogen we have, which would be an important measurement in its own right, we can do other things with nuclear magnetic resonance, or NMR. We can localize that signal using 1D or 2D or 3D images to see where that hydrogen is in the sample, and that's what we do in human beings. When we take a picture of somebody's head, as shown here, we take an image of where that hydrogen is in the person's head. Analysis, we often don't localize the signal. We're interested in the properties of the hydrogen. So I mean the signal lifetimes. So if, the signals we detect will have finite lifetimes, and lifetimes are known as things like T1, T2, and T2 star. And you've heard these from logging terms in NMR logs. But think of them as just simple signal lifetimes. And these we have is these signal lifetimes depend on the environment of the hydrogen. So by environment, I mean hydrogen is in a big pore versus a small pore, where hydrogen is attached to a small molecule or a big molecule, mobility of those molecules, all kinds of different things. That's where we get the information from NMR. So not just how much hydrogen, but we can tell something about the environment of the hydrogen, and that's how NMR becomes a valuable tool. So NMR tell us about rocks. There's any number of things that we can tell. Historically, NMR has been used to look at pore size distributions. So signal lifetime T2, if you will, tell us what the pore size distribution is, and I'll describe that in a little more detail in a minute. Now we can get bound and free fluids, clay-bound fluids. People have developed permeability relationships associated with that. It's really been the cornerstone of NMR use in the oil and gas sector since it was invented by, I guess, the folks down at Newmar in the U.S. And it can also be used for many other things, hydrocarbon typing. So these are things that are newer. Porosity, in other words, mobility of the hydrogen by way of molecular diffusion. And again, I'll get into more details on some of these things in a few minutes. And I'm a very good wettability indicator. So whether hydrogen is in contact with the pore wall and whether that hydrogen is oil or water can be indicated by NMR as well. I'll also describe a few advanced properties like how we can use NMR to assist in getting capillary pressure and those types of things. Let's look at a very simple diagram on how NMR can help us get, say, the pore size distribution, because historically this is what NMR has been used for. So look at the signal. This is what I meant by signal lifetime. So this is the detected NMR signal that we detect. And the signal from the hydrogen in a big pore will decay away very slowly. In other words, it will have a long signal lifetime. The pore will have a short signal lifetime. Well, what we measure is the summation of all of the pores. So this is the signal we actually measure with NMR at the bottom. So what we want to do is de-involve or get that information back out of that signal. So what we want to know is what are different quantities of signal lifetimes in that signal. And we do it with a thing called an inversion. You may have heard this again from logging space, but this is the inversion we take to detect what we detect, the NMR signal, and convert it into a distribution of exponential decays. In other words, a distribution of signal lifetimes. And this is math, and I won't get into the math, But to suffice it to say, this process can be quite difficult, and in fact, with this last term here, it didn't have many solutions. So what conversion does to converge on a solution is it adds an extra term. It's called a smoothing term, a regularization term, and this has led to some of the inconsistencies in the data because people will do this in different ways. What we want to do is we want to introduce a term that allows us to introduce dependencies on that exponential signal lifetime. So what I'm trying to say is, if you have a pore size that's 1 micron in a pore, it's very likely that we'll have a pore size, at least some pores that are 1.1 micron, right? So we don't just have an impulse response of 1 micron pores. It's good distribution of pores. So that information to converge this solution. So that's what the smoothing term does, is it forces neighbors, it forces solutions of neighbors to be related. Now, it forces the distribution to be smooth. And that's what you see here. So in this example, we have large pores, medium-sized pores, and smaller pores. So if we see the equations involved, this is the T2 equation. So this is the signal lifetime T2. And it's by this equation, or by the fluid. So this is the T2 property of the fluid. Also depends on the surface to volume ratio of the pore that is in. It also depends on the third term, which depends on diffusion, which is the mobility of that molecule, and experimental parameter TE. I won't really describe what that is, but suffice it to say we can make that short so that we can ignore this term. The bulk fluid is typically long, so this term dominates in this expression, which is of course what we want. So the property T2 depends directly on the surface to volume ratio. So when we look at this axis, we can assume that this axis is translated directly into radius or pore size. So in this distribution, subs here that are again and smaller as we go left. Petrophysics will tell us that as the pore size gets smaller, the capillary forces inside that pore will get higher. We'll get to a point where the capillary force cannot be overcome, and that fluid will be bound in the pore. So we call it capillary fluid. So what with these distributions is we apply a line, and we see pores that are smaller than this are bound. All the pores that are larger than this are free. So we have, in essence, divide this distribution up into two pieces. One free fluid, mobile fluid, and one being bound fluid. Shown here. So obviously where we place this line is quite critical. And I'll describe how we can do laboratory measurements to assist in getting the cutoff. Typically, logging tools will use standards based on the lithology of the well. So for instance, sandstones use 33 milliseconds as a standard. Carbonates use somewhere around 90 or 95. But in truth, that cut will depend on the reservoir. So laboratory measurements are needed to ground those cutoffs. Next stage of the process typically is to derive a permeability relationship from these NMR measurements, and these were done by Schlumberger and Coates at Newmar a long time ago. And there's typically only two that I know of that are well used. One's called the log mean or Schlumberger model, and the other one's the free fluid model. The first is permeability based on the geometric mean of the T2, and that's the average T2 value in the measurement I showed you above, and the velocity, and a coefficient, of course. The model depends on the ratio of free fluid to bound fluid, and Coates coefficient, or sorry, a constant. It's called coefficient. So in reservoirs, what we're able to do is divide this into free and bound fluid using a cutoff. We have the coefficient, we can derive permeability. And again, often we'll do laboratory measurements to refine those values for particular reservoirs. Say that in my experience, this first one is typically for gas fields. When there's more than one fluid, the free fluid model tends to work better. But that's not always true. A couple logs, because you may have more experience viewing logs. I'll just show a real quick log here, and this is a T2 distribution. Very simple sandstone reservoir, I believe. What we're able to do is we apply a cutoff, which is this red line, and we say everything over here is bound, everything over here is free. We then plot that on a trace, showing bound and free fluid, and apply the permeability relationships and predict permeability. And what we hope for is a good correlation between this and laboratory measurements. So calibrate the logs. How do we calibrate these values in the laboratory? Well, we do this quite simply with a couple different T2 measurements, if you will. So we'll take the rock and we'll fully saturate the rock with brine, and we'll do a T2 measurement. And we'll get something like the yellow line. This yellow line is the pore size distribution because it has only one fluid and it's fully saturated. We'll rock and we'll remove all the free fluid. And a number of ways we can do that. We can spin it in a centrifuge to force the water out. That's probably the simplest way. We could use flow cells, all sorts of different apparatus, but the centrifuge is typically the easiest way. So if we were free fluid and then do another NMR measurement, by definition, what we're measuring now is just the bound fluid. So the bound fluid is simply given by the area underneath this curve, or cumulative distribution. So the cumulative, I should have said earlier, is just the summation of this dark line at that point. So this represents all of the area underneath the blue curve. So we have free fluid. The difference is we have bound fluid. Is the free fluid. What we do is want the cutoff value to represent the area underneath the yellow curve to this line to equal the underneath the whole blue curve, and that will be cut off. So the trick people do is they go back to the cumulative till they hit the yellow cumulative and they come down. But basically, it's the area underneath yellow to the line equaling the area underneath the whole blue line, and that is the cutoff. So the exact cutoff for this specific rock, and of course we'll do many of them, we'll do statistical analysis to get an average value. In the example, you can see the cutoff is less than 10. And that's quite typical for tight gas fields. It will be substantially less than the 33 millisecond standard value. Of around 10 in tighter fields is typical. So what impact does that have on our analysis? And this is, again, a well in which we did a few different studies. If we use standard value, we'll get a bound fluid given by this value, which is very close, actually, to the porosity. So it's predicting most of the fluid is bound. When we do the measurements and refine that cutoff back to 10 milliseconds, we lower bound fluid, so we actually have a lot larger amounts of free fluid. And that's going to be important, right? So that's, in some instances, the free fluid level. Free fluid is predicted by almost a factor of 5 instances. Be a substantial impact when you're analyzing your logs. That's why we do laboratory measurements. Of course, as part of the process, we'll measure the permeability of each of these samples, and we'll derive those other permeability coefficients as well. I'll mention this because historically people have said that we don't see clays in these T2 measurements. And in the past that's certainly been true based on equipment limitations. We really haven't seen the clay-bound fluid. The parameter called echo time or tau, so you may know. But basically, as the instruments have gotten better, we're able to decrease that measurement time, and we're not seeing clays in these things. And the instruments definitely will see clays. Even in the logging tools, we'll start to see clays. So you have to be cognizant of what is the actual porosity you're measuring. Is it the effective porosity? Is it the total porosity? Is it an NMR porosity? So you have to be a little bit careful because the NMR porosity will include typically clays. And you typically don't want to consider these in the porosity. So it's just something to be cognizant of in some of the newer pieces of equipment. What we can do is we'll apply cutoff somewhere here and say the fluids with really short T2s are clay. We do laboratory measurements to ground that value because we can measure the clays quite easily in the laboratory. We do measurements on different types of rocks. The NMR measurement works in almost all types of rocks. We've done, have done, not just us, regular sandstones and carbonates, of course, but shale work is more recent, oil sands. Particularly with new equipment, the oil sands are showing some promise because we're able to see some of that heavier oil that we couldn't see in previous generations of equipment. This is a shale example. The shale example in a little bit. There's some more complex NMR measurement. The NMR, I think, is showing a lot of promise and giving us some insight into shales. In this example, we can see some of the fracture network. Measurement was done at with mining pressure. So if you added confining pressure, the fracture network would close up and you wouldn't see it. So the fracture network appears as longer T2s because it is as a large pore. So I point out that the situation can be quite complex. So one of the things that people will say is NMR is a very powerful tool, and that's true. And the reason it's true is because NMR is sensitive to many, many different things. So it's sensitive to viscosity, it's sensitive to wettability, it's sensitive to how much hydrogen, all sorts of things. Well, the biggest problem is it's sensitive to a whole bunch of things, right? So how do I get just one property out of it when all of these things tend to overlap? So, for example, I've kind of shown that graphically. This is first presented by Coates in his book. You may have seen it. But what we here, of course, what we measure in an NMR sense on these distributions is the envelope of these two things. I've just shown what is contributing by the oil and the water, by the different colors, the water being blue. So in an oil water wet case, we would apply a cutoff here. We'd say fluid to the left of that is bound, all the fluid to the right is volatile and wet. In a light oil water wet case. As we move to heavier and heavier oils, we're going to end up in a situation where that's no longer true. So we'd apply it off in the same location. The oil will now exist as short T2 values because the T depends on the fluid, not only pore size, but the fluid as well. So some of the heavy oil, if not all of it, will be predicted to be bound, and that can lead to interpretation, because indeed that heavy oil will move. Wet case is the same problem. When we go back to an oil wet case, we're okay because the fluid that's in those capillary bound is not oil. But again, heavy oil is generally always a problem, as well as mixed wet cases. So I present this as a problem, but it's also an advantage as well, showing you that I'm sensitive to wettability and viscosity as well as size. So we can introduce more complicated measurements to try some of that information out. And what we do here with this example is just show you how the NMR signals would change with the wettability of a rock. So what are we looking at here? Well, a simple pore in which it's wet. In other words, water is out here along the pore wall, and the oil in the center of the pore. In an idealized sense, you'll never measure this, but in an idealized sense, the NMR distribution is very short for the water and long for the oil. So the oil doesn't see the pore wall, if you will, because the water's in the way. So it'll be a very long component. We can take the same pore network and we add more oil. The oil will begin to see the pore wall. I know these are kind of loose terms, but it will start to interact with the pore wall, and the oil signal will get shorter in T2. No, it will move to the left. Of course, the water signal simply gets smaller. So the way is, during a drainage cycle, if we're adding oil to the sample and the oil signal moves left, we can say with certainty that rock is water wet. So there is a wettability indicator here. I've shown a real-world example in which we've done that. and this is detected oil during secondary drainage. In other words, we've already done the imbibition cycle, so we're adding oil to the sample. So we would start with the black, move into the blue to the red, and this experiment we did something unique, which we can do in the laboratory, which of course you can't do downhole, and that is the water we've used in this instance is deuterium oxide. So what is deuterium oxide? Well, it's just regular water, but the hydrogen happens to have an extra neutron. What does that do for us? From an NMR perspective, that particular type of hydrogen gives us no signal. So hydrogen becomes invisible. So we conduct the experiment so that we D2O, deuterium oxide. We won't see the water, we'll only see the oil. So we're not worried about overlapping peaks, as I described earlier. We can only see the oil. So of course, it makes everything easier to interpret. So in this example, as we add oil, the peak is moving to the right. Which means it's becoming longer, which means it's tending towards the middle, which oil is in contact with the pore wall, and then slowly moving towards the center of the pore as we add more. So it's slightly oil wet, and that was confirmed by USBM and other measurements. Let's look at some more complicated measurements. You may have seen these in the literature or on your logging tool, and these are known as 2D maps. And it seems to be, sometimes there was confusion associated with this because they're a little bit more complicated to understand. But think this way, what we have on this axis is one NMR property called T2, which I've already shown you in quite a lot of detail. In this case, we have diffusion. So diffusion, what is diffusion? Diffusion is the mobility of the hydrogen. Molar mobility. So at the molecule level, how well can that molecule move? Free is it to move? So as you might expect, a short molecule like water, the move is quite good, so the diffusion is larger. When you move to oil and it's in a longer hydrocarbon chain, the diffusion will get shorter. So in other words, it will get to a lower value. We use diffusion to help separate oil and water. Remember I showed you those overlapping peaks? For T2, if we measure diffusion at the same time, we can try to separate those peaks, and indeed you can do that. So to further explain these maps, because I have a couple of them, we have the T2 and diffusion. So if we look here at this point where it's bright, and this gives us an indication of how much hydrogen we have at those values. So now here we have a sum of signal. So the NT gives us the amount of signal that has this diffusion value and this T2 value. Right? So in here we would have signal that would have, say, 800 millis T2 and 1 times e to the minus 9 diffusion. So it's, to get the idea is that we can tell diffusion and the T2. If you set up all of these vertically, you end up with the simple T2 distribution I showed you earlier. So diffusion is very good at differentiating between oil and water because oil typically has a different mobility than water. Think of mobility like viscosity. Viscosity and mobility are somewhat interchangeable. This is a different map in which we've plotted two different properties again. So this is T2, but in this case we've plotted T1. And these two different lifetime signals, lifetime measurements, these T1 and T2 are signal lifetimes. I'll get into what exactly they are this way. T2 is what NMR people call the spin-spin relaxation, but T2 is affected by inhomogeneity of the magnetic field at molecular scale. In other words, things are very close to that hydrogen. T1 is called the spin-loss relaxation, and its scale is slightly larger than that. Now, they typically trend together. So, no, I'm sorry, the T1 scale is larger than the molecular scale. So its impact is further out. It's affected by surrounding molecules and environments. T1 and T2 are typically related in rocks. T1 is typically 1.5 times T2. Depending on rock, of course. typically the case. So here, this is actually a fresh state shale sample on which we've done this measurement. And what we're looking at here, because this is still very early on, is this is the water in the sample, because the T1 and T2 are very similar, and nothing else. And of course, this is what's piqued our interest, because this is definitely distinguishable and different than the peak. The question is, what is it? Well, what else is in shale that has hydrogen, right? If it's not water, you could argue it's water trapped in clay, but in likelihood that's not the case. Probably the organics or hydrocarbon. Now, I know this is a gas shale, so I know there's no hydrocarbon, liquid hydrocarbon in the reservoir. The hypothesis is this signal is the organics in the clay. So this is a good example of looking at the organics in shales. And I think there's a lot of promise. We've got to do some more research on this, and we will do that. But if this is the case, it's one of the few techniques in which we can do this non-destructively in shale. There's a set of experiments that, believe it or not, are probably even more complicated. They're called exchange experiments, and these are the T2 store T2 experiments. They're popular in carbonate reservoirs, and you'll see why when I describe it. If we have a rock which has two distinct pore networks, in other words, we have small pores and we have large pores, like we have in a carbonate, the connectivity between those pore networks is quite important to understand. In other words, does the fluid that's in the small pore ever see the big pore? That's important, of course, is storage in the small pore can be quite large. It can contribute 33% of the total porosity. But the permeability is going to be dominated by the connectivity in the large pore network. So how well connected the small and large pores are directly related to the production of the well. So the experiment is we perform those T2 experiments, and then we pause the experiment halfway, and then we continue. And if something happens during that pause, what happens is we end up with a T2 that's not equal to T2. What does that mean? Well, if we put a 1-1 line on here, if it lies on this 1-to-1 line in this experiment, then nothing really is happening during that wait time. Nothing happening, I mean, the splitter in the small pores are still in the small pores, and the hydrogen is still in the small pores, and the hydrogen that's in the large pores is still in the large pores. If from the small to the large pore, we'll begin to get a signal, as you can see ever so slightly here, off diagonal. And the intensity of this versus the intensity that stays on the pore can indicate the connectivity between the two pore networks. So it's a good method to look at the exchange between pore networks. From this point on, I'd like to describe a set or a different class of NMR measurements that focus mainly on laboratory techniques of resolving space. So utilizing the spatial resolution of NMR. In other words, we're going to try to tell where that hydrogen is coming from in these measurements. And we'll do things that I call perturbation then image. In other words, we're going to do something to the rock, and then we're going to do an NMR measurement, something to the rock, and do another NMR measurement. And we can, depending on what something is, we can tell things about the pressure. We just measure dispersion during flow studies. We can do imaging, 2 and 3 imaging in a traditional sense. So we can do imaging of people, we can do imaging of rocks. You get a little viscous fingering, flow fronts, all kinds of fun things. I won't describe that in this presentation. I just want to mention it. Of course, that is indeed possible. There's a new class of experiments, relatively new in the last few years, that is to do these 2D distributions I've shown you up to now, but actually resolve them in space. Now, we have one of these 2D distributions at each position, and I'll show you how that works here in a minute. This is a simple rock plug in which we've looked at the signal at different slices or positions down the rock plug. This is a profile. I would call it a one-dimensional image. The rock has been spun in a centrifuge, so one end of the rock has more fluid than the other end of the rock. So it was spun, so this end of the rock would all have air. So we have a rock that has a lot of water, and another end of the rock that has very little water. water. I thought that's where we were going with this. I'm sorry. The beauty of use, of course, is to know where that water is. Is it a big pore? Is it in a small pore? That was a lot more information than just how much water is there. And we can do that with techniques called spatially resolved T2. Now this rock is a fully saturated rock, so the T distribution is the same through the rock. So down this axis we have position, and on this axis we have a bunch of T2 distribution. I'll show an example in the next slide. Okay, so this is the same rock I showed you first as an image now. So on the y-axis is position, x-axis is T2, and the density is how much hydrogen we have with those particular values at those positions. So this rock that's been spun in a centrifuge and we placed it in the NMR machine, the outlet face is at the top. At the top we have lots of water, and at the end we have very little water. And not surprisingly, where we have lots of water, the big pores are occupied. The larger pores, the longer T2s are occupied. And at the inlet, those pores are empty. All that profound, but it's a good experiment to test the technique. In this example, we've just did a period of time and repeated the measurement many different times. If we did 145 hours, which is days, we end up with a saturation profile which is uniform. In other words, the same amount of water is it's at the inlet. The rock is now kind of equilibrium, if you will. What's interesting to note is even though there's the same amount of water at one end of the rock as the other, the pores occupied are still slightly different. So look at this end. This is preferentially in the larger pores as opposed to this end of the rock. And the rock is homogeneous. So this has to do with the centrifuge. So it may appear it's at equilibrium. I mean, I don't know whether this flue will ever enter and equal out. I haven't done the measurement after months, but you can see we can get information. It is applicable to many different types of flow studies, ER studies, wettability alteration, in which you want to do this measurement. Things I'd like to present is a capillary pressure measurement. It's something our company founded quite a time ago. And capillary pressure, again, I mentioned earlier, is that force that holds on to the fluid in the rock, so it's quite important. Traditional way of measuring capillary pressure in the lab, one's porous plate, centrifuge, injection, all which have their advantages and disadvantages. Injection is a destructive technique, but it's fast and expensive. It uses mercury. Capillary pressure curve you get from it has to be translated from a throat distribution. Porous plates probably considered the gold standard, but it's a very long experiment. For in a tight gas field, it can take a year or more to get a measurement. You're just kind of in the middle. We're using real fluids, but we use centrifuge forces to speed things up. And I think uses the centrifuge as well, so I'll just describe that technique in a little more detail. For traditional centrifuge measurement, we have a plug, we saturate it with brine, and we'll spin it in the centrifuge. We'll wait till water stops coming out of the rock. In other words, it reaches equilibrium. We'll win the average saturation in the rock. Hasselbner was nice enough to tell us what the inlet saturation was through this equation many years ago. I'll use some equations that I don't like, but they're Forbes and whatnot, in which they'll take that average saturation and predict the inlet saturation. So saturation and pressure, we have one line on a cap pressure curve. Like speed, we'll get another and another and another. So this tells us how much force is required to remove the fluid from the rock. In this experiment, we do 7 to 10 centrifuge steps, each one taking at least 1 day and sometimes 2 or 3. So the measurement can take 20 odd days. What we do in our NMR is we use the spatial resolution of NMR to speed things up. The same core plug, we spin it in the centrifuge, back to the same equation, but we realize quite quickly that can predict not only the pressure at the inlet, but it can predict the pressure at any point in the rock. So all it knows is saturation at those positions, and that's what we use NMR for. So we use NMR to measure the saturation at those positions. To be clear, we spin this rock in the centrifuge, wait for equilibrium, and we take it out and we put it in the NMR machine and measure this curve here. We know the saturation at each position, we know the pressure at each position. Now we have 30 or 40 measured data points per centrifuge speed, thus speeding up the measurement. So jump ahead a slide or two. Each colors comes from one centrifuge speed. So you see how we have many data points. In this experiment we did 4 centrifuge speeds just to prove the concept. The pink line with the squares is a porous plate measurement, so they correlate very well. We've done many, probably over 100 of these over the last 5 years, and they correlate very well. We typically only do 2 centrifuge speeds to fully on the cap pressure curve, thus making the experiment 3 to 4 times faster than what's traditionally done with the traditional centrifuge. Up one slide, what we actually measure, of course, in the NMR machine are these profiles, the pink being the fully saturated profile, and then each of these being the profile or the saturation after each of the centrifuge speeds. And we use the Hasselblad equation to compute the pressure at each of these positions. Just to show you a different example, this is a non-microdarcy rock. The trick here, of course, is getting enough pressure to remove the fluid. We only did 1 centrifuge speed in this case. The conventional centrifuge, we did 5, I guess, to do a comparison. And they correlate quite well. There is some differences here. You could argue they are, and we have hypothesized what they are, but I won't really get into them here. But they do correlate quite well. Another example, just to show you that the technique is applicable to doing imbibition and secondary drainage as well. This is an oil brine experiment on rock. And primary drainage, secondary drainage, drainage H the core done in imbibition, and the secondary drainage. That always comes up in this technique is what happens to the fluid after you remove it from the centrifuge and put it in the NMR. So that's fluid redistribution. Well, the answer is, well, I've already shown you an example earlier that tells you it doesn't stay put. It does move eventually. So the question really becomes, how long do we have to do these measurements? And the answer is, it depends on the permeability of the rock. The higher permeability, the quicker this fluid moves around. So in the worst case, where we have a Darcy rock, or so, we have a couple of hours to do the measurement, which is plenty of time because the measurements typically only take 20 minutes. So we've got a lot of these redistributions to look at the effects of this. The last thing I think I'll just leave you with is there's some extra information there that we can use, and it's a little bit unique to our technique, and that is, if we do a capillary pressure curve and we have lots of points on the capillary pressure curve, we can mercury equations backwards. So what do I mean by that? Well, at each pressure point, we can convert a radius. We measure the saturation change at that pressure because we have lots of data points. And we can get a curve, which will be pore throat distribution. Just a mercury in this case, and it correlates very well. Obviously, mercury can take us down to smaller pore throats, but we have a very good indication of pore throat. I mentioned that as something that is a little bit unique to this technique, is that extra information. Thank you very much.
Thanks a lot, Rick. So I think we can start the question and answer session. As usual, people sitting in the room can directly pose your question. From remote, please jot down in the chat your question. I will read the question, and of course Derrick will provide a reply. We should have a sort of interaction in course, and at best from remote. Please don't be shy.
Okay, break the ice.
Okay, Derrick, if you can show us. Yeah. Hi, I'm Nicola Bona of the labs. Derrick, please show us again the slide where you explained how the cutoff between free fluid and bound fluid is determined usually. The previous. Okay, again. The one with the blue and yellow teacher. Oh, okay, this one. So the common approach is the one you calculate the area underlying the blue curve and define the cutoff. The real world is different because if you look at the yellow curve, you see, for example, that there are pores having T2 of say 5 millisecond where there's free fluid. What if you put a cutoff at 9, you assume that all these pores in fact contain only bound fluid. So my question is there a better approach to take into account also these effects?
Yes, there is a different model other than the hard cutoff, I call it model, and that is, in reality we don't suddenly come up on a pore in which all the fluid's going to be bound, right? So not, 1 micron, all the fluid is free, and then we go to 1 micron and suddenly it's all bound. That's just not a reality in nature. It's going to occur. So there does exist a model which is called a spectral cutoff. In other words, we actually use an equation for the cutoff. It'll be a line which assumes 100% of the fluid is bound at the very short pores, but then will slowly come down into the large pores, called a spectral cutoff. And what we do with that is we take that line and we would then multiply it point by point with the yellow line to derive the bound fluid. So it's a gradual cutoff, if you will. It's given by a weighting function or an equation. And that's, people have used that. I guess you might ask yourself, why use it? It is a more realistic model because it's mostly what's happening in nature. But at the end of the day, hard cutoff and the spectral cutoff will give you the same amount of bound fluid. So if really only after what is the bound fluid, then the cutoff can give you the same number in a much more simple sense.
One question, sorry, Maurizio Mele. You have mentioned that you recommend or suggest for fluid typing 1/T2 maps for fluid typing in gas shales. If I understand. If I understood. Do you think that the total amount of fluid in a gas shale system is enough to have a good signal for having these kind of fluid typing maps?
Asking is can NMR see enough of the fluid?
Yes, because in a gas shale system, the fluid that can be activated by NMR is small.
Yeah.
Do you think that the signal is enough is to have this kind of good typing with the T1, T2 mapping?
Yeah, it's interesting you should mention that. So the additional type of logging equipment, the logging tools are going to always lag behind the laboratory equipment. So we do a better job in the laboratory than you can do in a logging tool. So historically, the logging tools couldn't even see clays, right? So now getting to the point where they can see clays. When they start to see some of these very short pores that are in shales, there is fluid in the shales. The question is, can we see them? Yeah. The amount of fluid is very small. The amount of fluid is very small, and the pits they're in are very small, which from an NMR standpoint means the T2s are very short, which makes them difficult to measure. So in actual fact, there's actually a large amount of fluid that is in the pores, but often the tool can't see it. I just stated the existing logging tools. I know the companies have come up with different techniques. They've pushed ultra short TEs and all that sort of thing. And the whole goal of all of these techniques is to start to see some of those things. I've experienced with the logging tools. What I can tell you about the laboratory equipment, the new generation of laboratory equipment can definitely see those signals. Which in mind means if the tools aren't there yet, they will be, right? So I can't answer it directly. I guess the question is, I'm not sure whether the logging tools can do it. I know lab equipment can.
Thank you. Facility from the lab. You mentioned that you can separate or distinguish the oil from the water with NMR. So are you able to calculate the saturation of the fluids inside the core? I mean, they are at the end of a core flooding or the initial water saturation.
You did mention, I mean, in order to distinguish between fluids, oil and water, the oil and water need to be different from an NMR standpoint. So if you have a light oil that's very water-like, then its diffusion coefficient will be the same, so that we can't distinguish them. So in some instances, we can see them, the differentiation. And where we can, yes, we can quantify how much oil, how much water. So we can look at the oil saturation and the water saturation. In laboratory, you can do additional things if the oil and water signals have NMR properties that are similar. I showed you one in which we use 2O for water, which makes it invisible. That's one trick we do in lab. Another trick is we can use doping agents to move the T2. So we can put, I don't do any of those things. I'd rather use the actual fluids, but so we can separate them. Yes, we can quantify, but it depends on the oil.
Marco Pirrone from Reservoir Characterization Department. It is very interesting the point that you mentioned about the regard to the question by Maurizio. And so you say that in that kind of plot you are pretty sure that maybe one of the signals can come from the hydrogen, the gas, okay, in the shale. Is it right?
The T1, T2 map?
Yeah.
In this example, I haven't done that. I mean, earlier in the week, T1 and T2 will be different for gas as well. So if we had gas in the system, the signal would show up here.
That's the question. Because
in your logging tools, that's what you see.
Yeah, because sometimes for a logging tool, the first problem is to polarize the gas because we have not so much time to wait the hydrogen to wait. The hydrogen will be following the magnetic field. Or the other problem of the hydrogen in this is that we know about the gas that will lower the signal of the gas. And sometimes, since we are often log with the short TE, so short echo spacing, about 0.2 milliseconds, also the duration of the gas will be hopefully restricted. So I should expect that the gas will stay in the right of the
up here.
Yeah, exactly. So it means that maybe in a shale, differentiation mechanisms are related to the gas, because it is absorbed or something like that. That can.
In a shale, gas is going to be a little, well, can be substantially different, right? Typically, T1, T2 maps on logging tools in the past have been used to distinguish between gas and fluid. As you mentioned, the T of the gas will be long, so it will exist up here somewhere, and the fluids will be down here, so we can distinguish how much gas, irrespective of whether we're polarizing or pollution times, and there's other questions involved, but the gas will be here. In a shale, gas isn't really just sitting in a pore, right? The gas is usually in a Carrigan network or in the organics. And that question becomes, what state is it in those organics, right? As the pressures come, is it actually gas anymore, right? Is it liquefied? Is it on the pore wall as a liquid, right? I mean, that's what some people think. I don't know we have all the answers yet, right? And that's, to be honest, to be able to to answer that. I wouldn't expect shale to get a typical gas T1, T2 response. I wouldn't expect that. But you could do a laboratory. I haven't done that, where you just introduce gas into this rock in a pressure cell and look at the signal.
Yes, so the important point is to try to reproduce the reservoir condition, because otherwise maybe we can misinterpret the results.
No, yeah, reservoir conditions are very, very important, especially when dealing with gas, right? I mean, this is a native state rock. It won't have any gas because we release the pressure, the confining pressure. If we reintroduce gas into this system, which we can do, start to see the gas in the laboratory just as you do in the downhole tool, and those would be a useful set of experiments to do.
Okay, thank you.
Any further questions? Even remote? Okay. We can close the session. Thank you for coming, Mr. Derrick. Of course. I hope we can have some more chance to have you here and have some more kind of events. Thank you. Thank you all. I remind you all the people that this kind of webinar will be is of course recorded, and registration will be ready more or less 3-day working time on our Reservoir Cup and Lab Cup website. So thank you for coming.
Thank you.
Derrick Green. Thank you, Nicola, and all the attendees here in your remote. Just the last thing, we're going to have another webinar from in Venezuela next week in the morning, more or less 9 o'clock. Of course, see you then on the screen and here. Bye.